Okay, so I'll start with a quick recap of what we were doing last time and then carry on and tell you what we'll do today. We proved certain things. We proved that the volume of the d-dimensional sphere, all points of length less than or equal to 1, goes down as d goes to infinity, and in fact the asymptotics is some constant to the d divided by d to the d over 2, and so it goes to 0. And to do this, we used the Gaussian integral, and we needed two I won't go through the proof again, but we needed two properties of the Gaussian or the integral. So one was radial symmetry, so it depended only on r, the distance from the origin, and two was it splits into the coordinates. That's only the Gaussian that can do that. So even though it looked like I pulled this function out of the hat, it was for a reason, right? And we proved also that for a uniform random point x from the unit sphere, we have that the probability that the length of x1, the first component, this is the distance from the equator, if you will, is greater than c over root d, goes down as e to the minus c squared. Okay? So we proved that. So here's a little sort of general thing I didn't state last time, but many quantities like x1, the absolute value of x1, right, the first coordinate, is a random variable when x is picked uniformly at random from the unit ball. Such random variables have very well-behaved tails. They have exponentially dropping tails. That is to say, so they drop off exponentially as we move to multiples of the expected value. So as soon as you take twice, thrice, or c times the expected value, it goes down as e to the minus c or e to the minus c squared. Okay? Often e to the minus c squared. So the e to the minus x squared is an important function because it's a Gaussian, right? And we'll see that several times that'll come up. So I sometimes call this the law of large dimensions. It's like a law of large numbers, but basically having many dimensions is sort of like having many independent variables sometimes. So behaves like that. Now, 2 gives another proof of 1 and also leads to some puzzles that we discussed a little bit, but it's worth understanding. So by union bound, we saw that at least half the volume of the sphere lies in a cube of this side, and we draw a picture, and the picture looks sort of confusing in a way, because all I'm saying is here is a cube, and half the volume of the cube is here. But I already proved that half the volume of the cube is also there, right? So apparently they don't seem to intersect, but they do. Of course, they intersect. Both facts are true. And you should just write down algebraically what happens, and you'll see that that's not a problem. Okay. So 2 also implies, this equator also implied that samples x and y from the sphere are nearly orthogonal if they're independent. And we proved that for many samples. Okay. And we also saw how to generate uniform random points from the hypersphere using Gaussians. The intro to that was rejection sampling will not be good, right? Because the cube is much larger than the sphere. In fact, that's a general phenomenon in high dimensions. If you want to do uniform random samples from a lot of other things, which got here, right? You cannot do rejection sampling. In general, in d dimensions, you cannot enclose even a sphere, let alone other objects, in some enclosing thing which is nice and not much greater volume. Okay? In 2 and 3 dimensions, you can put it in a square or cube, and from which you know how to draw samples because they're independent coordinates, but you can't do that in high dimensions. Okay? So that's a recap. Now today, I'm going to start today's lecture. Today, basically, I'm going to prove a concentration results for sums of random variables. It's probably pedagogically, I thought a lot about what's the right result to prove, from which I can derive all the results that we need, like Chernoff bounds. I'll tell you what they are if you're not familiar. Chernoff bounds and other concentration things. So I'm going to tell you that. But first, let's just start with the central limit theorem, right? I'm not going to prove this. I mean, you've probably all seen a proof, but at least you should know the statement. So if you have independent, identically distributed, they don't have to be identical. That's not that important. Independent is important for this. the expected value is 0, each of them, the variance is sigma squared, then the quantity, right, 1 over root n is the right normalization. That is because if I sum these n things, variance just sums up, so the variance of this is n times sigma squared. If I divide by root n, the variance becomes sigma squared, right? So it tends to, in distribution, it converges to the normal with mean 0 sigma squared. Okay? This is only a limit statement. What we are going to try now is to get statements that hold for every n, because for us to use, we need that. Further, this limit statement has some problems. It's not a uniform limit, so it's generally not immediately useful. But that's going to be the guide of what we want to get, right? Central limit theorem. So one remark, you cannot get this if only the second moment is assumed to be finite. Central limit theorem needs only to assume the second moment is finite, right? So the third moment need not be finite. So, for instance, if you have the density, the probability of random variable x equals x is c over x cubed. Sorry, plus a little bit. Okay, that has a finite second moment. That's fine. It doesn't have a finite third moment, but that's still for x greater than 1, let's say. Okay. That's good enough for the central limit theorem. It's not good enough for us. So to get this going, it is not sufficient to assume just second moments. For that particular density, it's a power law. You can see what happens. I won't do it here, but you can do a calculation to see that, in fact, you don't get very nice tail bounds. You wouldn't get. That's a polynomial. The tail is very fat, right? So you won't get very good tail bounds. So, okay. So we are going to look at. So most of the lecture today I'll spend in tail bounds, and we'll come back to geometry either at the end of today or the next lecture and start looking at Gaussian annulus. But this tail bound is going to be quite useful, right? First, Markov inequality. Just to recap, you have a non-negative real valued random variable, then the probability that is greater than t is bounded by something that goes down to 0 as 1 over t as t gets larger. And the proof is just that. We have no cancellation, so the expected value of x is at least what you get from things that are greater than t. Okay. It wouldn't be true if the function, if the random variable can take negative values, that could cancel it out, and this is not true, right? So it's only for non-negative, and then Chebyshev, you know, is just saying that the deviation of the mean is bounded by that, and the proof is just by applying, take the square of this and apply, which is non-negative, apply Markov. And here the tail bound goes to 0 as 1 over t squared as t goes to infinity. Okay, instead of t, you get 1 over t squared. Now, can you do better? Can we get a tail probability that falls off more than quadratically in t? Falling off, I should have said here, more than quadratically, right? Faster than quadratic. And in fact, a simple thought shows you that higher moments would help. So moments are going to play a key role in this. It's often, these tail bounds are not always, of course, traditionally they were, but not always proved by taking moments, but I'm going to do that here. So higher central moments, so if you take the rth moment, think of r as higher than 2, right? Take the rth moment, so you get 1 over t to the r. That is just by applying Markov inequality to the random variable x minus ex, absolute value to the rth power. Usually we want to apply it with r even, so we don't have to worry about the absolute value signs. I'm sorry, we don't have to worry about the absolute value signs there, right? If r is even. If r is odd, it's, you need to put that, but think of it as being applied when r is an even integer. Of course, r doesn't have to be an integer. It's true for any real r, right? So the higher the r is, the greater the rate of fall. You get 1 over t to the r. Okay. So that quantity doesn't depend on t. 1 over t to the r does. And if r is very high, then you get a very steep fall. But for that, you need to bound higher moments. you need to bound higher moments. So we'll see how to do that. So I'm going to state now what we call in the book the master tail bounds theorem, only because it's going to imply tail bounds for Chernoff, Gaussians, exponential, and all other things. Traditionally, there is a particular proof for Chernoff bounds. I'll go over that in a minute. Some of you are familiar. But then that doesn't work for Gaussians. That only works for bounded random variables. So traditionally, every one of these one proves separately, but this is going to give us all of them. That's the reason for calling it master. So you have independent random variables, mean zero, variance at most sigma squared. Not identical, right? For those that are interested, this actually holds even without assuming independence. It holds in a more general context. It holds for martingales, but right now we'll only look at, here we'll look only at independent things. So I'm going to take some integer s, which is less than n sigma squared over 2, for whatever reason. And here's the crucial assumption. I'm going to assume the rth moment. If r is odd, this could be negative, so I put absolute value signs. Does not grow faster than r factorial. And this r factorial is crucial, and I'll tell you in a minute why. So this lecture is going to be fairly technical because I'm going to have to prove this, right? So, but the point here is moments only grow as at most r factorial times sigma squared. Number one. Number two, I don't assume all moments exist, only certain up to a limit. So it's possible that beyond s, the moments don't exist even, and certainly not necessarily bounded. So the gist of this is the rth moment grows at most r factorial. And the theorem, this is the theorem, now we'll prove this, which will take us a little bit of time, we'll prove this, is a tail bound, the probability that x greater than any number a, provided a is not very big, very large deviations, this is not valid, but as long as a is at most this, falls off as e to the minus a squared times something. Okay. Let's stare at that something for a little before we prove this. So each of these random variables had variance at most sigma squared. If I add up n of them, the variance is n sigma squared at most. So an upper bound on the variance, that should be x1. Upper bound on the variance of x1 plus xn, because they're independent. So if I did have the central limit theorem type behavior, then this is correct. I would have a squared divided by the variance. Okay. I'm not worried about constants. The 12 is higher than what central limit theorem will give you. We'll give you 2, but we're getting it for all n. So within constants, it is like the behavior of the central limit theorem. Okay. So in some sense, the tails behave like this. Now, they don't behave like this for very large a, but that's always going to be true. So you should always revisit this little thing, that if I have coin tosses, if I toss a coin, if I toss n coins with probability of heads being p, so this is Bernoulli p, each of them, then the tails of sum of xi, 1 to n, are not Gaussian beyond a certain point. So cx squared beyond some x. So very large deviations, you get only simple exponential bounds. That's always going to be a problem, right? Again, that requires a calculation. Actually, it doesn't require too much of a calculation. The probability, so in fact, I can write this down. The probability that xi is greater than or equal to n, that means all the coins have to come out to 1, right, is p to the n. Whereas if it had been sub-Gaussian, you should be getting an n squared there, which you don't get, right? You'll only get an n. Let's see. So this is a Gaussian bound with a correct variance, except for constants. You get that. Now, why the r factorial? Okay. This I have to write on the board because I didn't write that. So intuition about the r factorial. So many proofs of tail bounds start by saying the probability that the random variable x is greater than or equal to t, right, equals the probability that e to the lambda x is greater than or equal to e to the lambda t for a positive lambda, for all positive lambda. Okay. This is true just because the exponential function is monotone, right, which is less than or equal to the expected value of e to the lambda x minus lambda t. This is Markov inequality, right? Who has seen a proof that begins like this? Okay, yeah. This is called the Bernstein method, or the exponential generating function method. It's used for Chernoff, for instance, right? So many proofs start like this. Now, if x is sum of xi, 1 to n, so that's x, and then this factors. That's e to the lambda x. X is the sum of xi factors, right? It's just a product. I won't do that proof, but that can only work if the exponential moments exist. Okay? This is valid only if expected value of e to the lambda xi exists. Otherwise, it's not valid. And now, if I expand e to the lambda, I'm sorry, I should have put that in the slides, but anyway, so I do a Taylor series of this, right? So then I will get, I use t already, so I get I equals 0 to infinity, lambda to the I over I factorial expected value of x to the I. I'm just doing exponential Taylor series. So if expected value of x to the I grew faster than I factorial, there's no hope. This series does not converge, right? So this method is, I mean, it may work for other reasons, but this method is not likely to work, right? There may be cancellations, but it's not absolutely convergent. So if this grows faster than, so if grows faster than x to the I, then I factorial, the series does not absolutely converge. No absolute convergence. So then the Bernstein method, this is called the Bernstein method. Again, I won't follow this method. I'm going to tell you that it's better to abandon that and go with moments. That's the spirit of this theorem. But if you want to use Bernstein method, it better be true that it's bounded by I factorial. Actually, it should be bounded by something slightly less than I factorial. Yeah, so yes, for lambda less than 1. So there is some play with the lambda, yes. But, okay, so yeah, there is some play with the lambda, provided, I mean, if it goes actually strictly faster than I factorial, you're sunk. I mean, if it grows. So if it is I to something greater than 1, okay, then you would be in some trouble. Yeah. So, yeah. So if it's substantially more than I factorial, then you would be in trouble. Okay. So the R factorial it agrees with that. But most importantly, that statement, this method, only works if for every I, however large, it's bounded by something like I factorial. Whereas here we assume only finite moments, right? So this is very crucial. So I want to, so typically in this we will encounter what are called long tail densities. Long tail just means the tail is not exponentially going off. So for instance, if you had something, everybody knows what a power law is. Power law is just polynomial decay of the density. If you had a power law, this is still valid. You have finite moments, but you will not have very large moments. So this is useful even when there are finite moments. Okay. So I'm going to take, it's going to take some time to prove this, 4 or 5 slides. We're going to go over the proof. It's elementary. There's nothing phenomenally sophisticated going on. There's some combinatorics and it's elementary. Was two. Thanks. So the idea is to prove an upper bound on the rth moment and then use that for the sum. Okay. Then use Markov inequality. Okay, so the sum is this. To expand this, you do the multinomial expansion. We start with the multinomial expansion, so we get that. So this is just sum over all partitions of R into R1 through Rn, right? Is the exponents of x. I mean, it's how many times when you expand this xi occurs. I've just done the multinomial expansion, right? And that is that. And I now take the expected value of both sides. I want the expected value of this whole thing, and I want to take the expected value of this. Okay, and something nice happens. So let's try to guess what nice thing happens, and then we'll see it. A lot of these terms have zero expectation. So which terms have zero expectation? Sorry? Yeah, whenever Ri is 1, right? So any time an Ri is 1, independent says that the expected value of each thing splits up. I'm writing all this down in a minute. But if Ri is 1, the expected value of xi is 0, because we started that, right? So where Ri ranges are all non-negative integers summing to R by independence. So first we have to peel off the terms. Independence says that they factor out like that. Okay? And then we get, if in any term Ri is 1, the term is 0, since that's 0. So Ri is either 0 or at least 2. Okay. By the way, in all these proofs, that's crucial. If Ri equals 1 terms were there, then you would not get this kind of result. You would not get Gaussian behavior. So, okay. So now we are going to do some combinatorics to figure out how many terms are alive. So let's consider all of the terms where each Ri is either 0 or 2 or more, because we are only interested in those. We are not interested in the terms where Ri is 0, Ri is 1. Okay. Every Ri has to be 2 or more if it's non-zero. So I assume this R factorial. So the expected value of R, this is from the last slide. There was, so if I raise to the Rith power, I get only Ri factorial. This was a hypothesis. This was an assumption, right? Therefore, that cancels out, and you get this. So this actually, J is in the subscript, and you get sigma to the. So this is not a minus sign. Okay, so maybe I should write. It's sum over something, sigma to the twice number of non-zero. All right. So that's because every time Ri was non-zero, we assume the bound is at most that. See, this is what I'm applying. You get only a sigma squared every time Ri is non-zero. It's important, by the way, that sigma squared, it doesn't go up as sigma to the Ri. We'll see all of, I mean, some thought is required to make sure that all of those are important, but later you can think about that, right? So collect terms which have t non-zeros, because they have the same power of sigma, and call them this. This is the set of n tuples that have t non-zeros. This is now combinatorics. And then you get expected value of x to the R is this. This is what I'm trying to bound. So everything that is t non-zeros contributes sigma to the 2t, right? So, and there's an R factorial a little outside. So we have to do all that. Okay. Again, as I said, this lecture will be technical. I think there are maybe 2 more slides. So we bound, we crucially have to bound the number of R1 through Rn n tuples adding up to R, where it's at most t of them are non-zero. First of all, which t you choose first, n to the t subsets. One of them is the t that you've chosen to put non-zero Ri's on. Once you fix a subset as a set of t values which are non-zero, okay, each of those values is non-zero, so it must be at least 2. So we allocate 2 from our budget of R to each of these Ri's, and then the rest are allocated arbitrarily. Again, this is combinatorics, right? So what is this? So let's go with this. The 2t, I already have to give each one 2 at least, so I give 2, so that's, I'm left with R minus 2t, and I must partition the R minus 2t into t minus 1 parts. I can arbitrarily allot any number to each of the parts, and that's what I get. Okay. There's the number of t tuples. There's no permutations here because these are not labeled. You have to think at home, make sure that the proof is correct combinatorially, but obviously I've checked that. So you get that j of t is at most this much. It's not a precise estimate, but it's at most this much. Putting this together, you get that you get this term for that. Now we'll prove. So t only goes up to R over 2. Important. It doesn't go up to R. It goes only up to R over 2 because everybody which is present at least as 2 at the level 2, right? So there are R over 2 things. We'll prove that t equals R over 2 is the max of this. So this more or less is going to only look like R factorial times if I put t equals R over 2 there. So we get n sigma squared to the R over 2 divided by R over 2 factorial, 2 to the R over 2. Okay, all I'm doing is putting t equals R over 2. Now, if you use Stirling and other things, this is R to the R over 2. So we get n R n sigma to the R over 2, another 2. Okay. We'll do this manipulation in the next slide. But the moral of the story is very important. The moral is the rth moment of the sum grows only as R over 2th power. Okay. Now, it requires some thought, and I will do it in the next slide. I'll do the manipulation next slide. But that is essential for sub-Gaussian behavior. So this is essential for e to the minus x squared. That square there comes from the R over 2. So if I didn't have R over 2, if I just had R, which is what I would get trivially. So remember, I'm bounding expected value of xi to the rth power. Okay. So there are n to the r terms, n choose r terms. So I might be expecting an R there. If I did, I would not get Gaussian. Okay. Again, it requires a little bit of manipulation at home to make sure that you see that. But I won't do the manipulation, but I'll tell you that R over 2 is crucial. Okay. So now I want to prove that t equals R over 2 is the max. Okay, so that's the manipulation. For t less than R over 2, it's easy to see that ht is an increasing function, is increasing well enough, fast enough by a factor of at least 2 each time, and therefore the sum is what happens at R over 2, then as you go down from R over 2, it's falling off geometrically. So that's only a constant. At the end of the day, you get this, which is what I wrote down there. Okay. So what have I got up to this? I've got the most crucial thing I won from all of this calculation is that the exponent is R over 2, not R. Okay? And that's what is going to give us the sub-Gaussian behavior. And then you just apply Markov inequality to get this. Again, you have an R over 2 at the top. Okay. Now, I wanted e to the minus a squared, but I've got the rth moment, and it turns out that's another standard calculation. This moment bound applies to every moment r less than or equal to s. If you remember the proof of Chernoff, then those bounds applied for every finite r, and you choose the best one. Okay? That's what we're going to do, except we have a restriction. R cannot go very high. Okay? You cannot get arbitrarily high moments. Okay? And then we do some calculus and take r to be the largest even integer less than or equal to this. So this function is minimized at a certain r, which you can find by calculus. You take the log of that and minimize that. You find by calculus. On the next slide, we'll see that. And then r is basically taken to be that value. And that value turns out to be less than s, so it works. So this is a statement that says all of that. So we have a function that looks like x to the x over 2. And you take log and minimize. Then you see that minimized at that point. Just differentiate, set it to 0. It's minimized at that point. So instead of 2, we're using a 6. And then at that point, you get that you plug the minimum value in, you get this, and which is at most a squared over 12 n sigma squared. That proves the theorem. Yeah? You have a question? No. So you do have to check all the details. I mean, there are several calculation details that you have to check, but at the end of the day, we end up with that. Okay? So that proves the master concentration theorem. I'm not going to give you all the implications. I'll give you 2 implications of this which you'll use. One is Chernoff. The other one, which comes next, is the Gaussian annulus theorem, which we'll need for a bunch of, which we'll use for. So I think I'll be able to prove this and the Gaussian annulus theorem today. We'll use the Gaussian annulus theorem for the random projection theorem. We'll see the next week, which is Johnson-Lindenstrauss. So we'll crucially use that. Chernoff bounds. How many of you know Chernoff bounds? Have seen Chernoff bounds? Many of you have seen, right? So, okay, so we'll derive that as a corollary. So if you have independent Bernoulli random variables, here there's one small restriction for this to be applied directly, is that p is not very close to 1, the probability of heads. Then qualitatively, the bound says the probability that it deviates by more than n times p is this thing. Again, you cannot do very large deviations. Only for c at most 1 is this valid, right? So the c squared behavior stops for a certain c beyond. So it's got to, c has to be bounded. Okay? And you get it simply by applying, the moments are good. So simply by applying the master tail bound theorem, you would get that. So you first center it so that the expected value is 0. The variance we all know is p times 1 minus p. But the moments are also bounded by basically that. The moments are also at most p times 1 minus p. This actually, I wrote down a proof, but it's actually simple to see, right? Beyond the second moment, xi is at most 1 anyway, so that's going to be true. Okay? We need bounds on moments for our theorem, right? So this is all going to be true. So apply this theorem with A is the C and P, how large a deviation you have. Okay, I think that's all I've said here. By the way, there are more details given in the book, right? So than the slide. Okay. So the usual proof of Chernoff bounds, again, is by going through the Bernstein method, which we erased, is going through the exponential moments, right? That's what we do. They do apply in this case. Exponential moments do exist because these are finite random variables. They never exceed 1, so the exponential moments certainly exist. Okay. Now, the next thing I'm going to do is the Gaussian annulus theorem. I'm going to state that first. The exponential moments also exist here, but I'm going to give you a proof just based on the, but the random variables are not bounded, right? They're Gaussians. They can go to infinity. So some notation, you have a d-dimensional spherical Gaussian. This is the mean of the Gaussian is now bold-phase 0 because centered at the origin in d dimensions. This is the identity matrix, is the variance-covariance matrix, right? So for Gaussian in higher dimensions, you describe it by mean and variance-covariance matrix. So I is the variance-covariance matrix. In statistics, it's called sigma, right? I mean, statisticians are notorious for their notation, so they use sigma for, it's a terrible thing to do, but they use sigma for variance-covariance matrix, right? So it could be more general. It need not be identity. But in this case, identity, which means the level curves of the density look like this, right? I mean, so actually, so I should say, the density corresponding normal 0I is e to the minus x squared. There's a normalizing constant, 2 pi to the d over 2. So the density is maximum at 0 and falls off. Okay, and the assertion is for any beta which is less than root t, at most so much of the probability mass, again notice the beta squared there, lies between root t. So most of the mass lies between root t minus beta and root t plus beta. So, oh, maybe I should put up, excuse me, I should tell you one more line and then draw a picture. So, intuition, so the expected value of the length squared is just the sum of d things. Each has expectation 1, normal 0, 1, so that's d. So the mean squared distance is d. Radius, let's call radius the square root of the mean squared distance, is root t. And it says that it should be concentrated about its expectation. That is roughly what this is saying. So let's see what this is saying. So it's saying that with high probability, this is between root t plus beta and root t minus beta. So x squared is between d and order root t. If I expand this, right, if I square this up, the second term that's more significant is beta times root t, and then you get beta squared, which is a small order term, so this is more significant. So if I draw a curve, so this is a distance root t, and the annulus is width order 1. If I instead have normalize it so that this is distance 1 for the Gaussian, the annulus is distance 1 over root t. So this is different from the sphere, right? The sphere was concentrated in a smaller annulus, 1 over d. This is concentrated only in an annulus of width 1 over root t. Well, of course, it is true that there's a sum of independent random variables, so you expect it to be concentrated about its expectation, and that's what we'll prove with this, with our theorem, right? We oh, it's going faster than expected. We are already at the 12th slide out of 13. So, any questions, or anybody wants to ask questions? Let's take a break and drink water at least, right? Yeah. Everything okay so far? Okay, so I'll go on. So, what are we doing now? So we are just doing the r is the radius. We want to make sure that 8 minus root t is at most beta, and if it is not, then you also have this, right? And that's greater than or equal to beta times root t. But r squared minus d now is the sum of independent random variables. which with mean 0, right? y1 squared is from there. Mean 0. Each of them is mean 0, and they're independent. So put xi equals yi squared minus 1. The probability that xi is greater than or equal to beta minus t is what we want to bound. Okay. But we need to do the nth moments of xi. So we have to bound moments of Gaussians. I mean, this is not a big deal against standard, but let's try to do that. So, okay, either yi is less than 1, then xi is at most less than 1, any power, or yi is greater than 1, then xi is that. So in any case, in either case, we have that. I've added both cases, basically. So when I get that, and that, I'm just writing down the Gaussian moment, right? And I make this substitution. You compute the moments by converting into, this is a gamma function. Okay? Because we get either minus z and z to some power. That's a gamma function. Right? So we get 2 to the s times s factorial. Okay? So the variance is at most 8. It's a fixed number, constant. But we do not have that the nth moment. So for the theorem, we wanted the nth moment to grow only as s factorial times the variance. Okay? That's not true because it grows as, where is it? It grows as 2 to the s times s factorial. So the expected value of xi to the s, 2 to the s times x factorial, but would like no 2 to the s. Right? We want just s factorial. We don't want 2 to the s growth. So how will we avoid it? I mean, we cannot avoid it. I mean, it is quite, there is a something to the s here, because that's how the gamma function is, right? So up to this point, up to the gamma function, it was exact. Well, except for the 1, this was exact. So I cannot get better than that. But 2 to the s is lower order than s factorial, right? S factorial is roughly s to the s. 2 to the s is less than that. So it should be manageable. So what might be a trick? I mean, so what shall I do? So maybe I can ask you that question and then try to do it. So I would like random variables, nth moment, to grow as s factorial, basically. But this is growing time as 2 to the s times s factorial. So what's a good way of trying to do something? So I just divide the random variable by 2, then the 2 to the s goes away. But a factor of 2 is not a problem because we are very generous with constant factors. We don't care, right? So that's what will happen. We put wi is equal to xi over 2, and everything goes through. Okay, so now, since there are no questions, there are 15 minutes. We'll have to go over new stuff which I can do on the board. But if you want, you can ask questions instead. Okay, so now I have to write on the board because, again, I'm going faster than I expected. So what Chiranjeev is asking is that, so now if x1 through xn or normal 0, 1 independent IID, then I would like, let's say, the tail bounds for so these are independent also, and the moments exist, and we should be able to get a bound for these. So that's indeed a good point you bring up in a way, because for sum of squares, it's a standard thing to try to derive bounds. This is probably less standard. So, but this also the moments are still nice. So this also follows. Yeah, so you do get. So I have to work that out to get what we get.
That's what I told you. It was difficult to get there.
Okay, we'll work it out. So next time maybe I should work this out and then bring it, right? So instead of trying to do, but it's fair enough. It's a good question. So I mean, because this should apply and get you a bound for this norm also, because these are just independent and sum of independence. So it'll be more exact than 2 to the s times s factorial is just a bound. But qualitatively, the 2th moment of normal Gaussian is like S factorial. Well, it's odd terms only up to 2s. But, yeah, but the leading term is s to the s. The c to the s times s to the s. Because you have s things you're multiplying. Right, you're multiplying 1, 3, 5, and so on up to 2s, or 2, 4. But there are s things you're multiplying. So it's at least like s to the Stirling's formula or something. It's s to the s times the constant to the s. Qualitatively, that's the correct. So let me introduce Johnson-Lindner-Strauss, which we won't start proving. We'll prove next time. So the idea is you have points. Let's see, how do we denote them? x1, x2, up to xn in Rd, n large. There are many problems in which this is used, but I want to start with one concrete problem, which is estimate all pairwise distances. There are n squared of them, and if I take a pair, it takes d time to find the distances, right? There are d coordinates, I have to subtract them and add. So it would seem to take this much time. This theorem, what the Johnson-Lindner-Strauss theorem says is that if I have 2 points, just 2 points in D space, I can project them down to a much smaller dimensional space. Okay. So that the distance between them in the projection gives you a good estimate of the distance between these two. There's a known scale factor, but for that, it's almost exact. So let's see what we expect here before we go on. So I have this point, let's call this point x, this point y. I want to estimate xi minus yi squared. So first intuitively, and then we'll do the actual proof next time. Suppose we choose a random coordinate system. Random coordinate system just means I take the regular coordinate system and rotate it by a random amount. Okay? Another way of saying that is I pick the x1 axis uniformly at random, and then x2 axis uniformly at random perpendicular to x1, and so on. So if I took a random coordinate system, intuitively, the xi minus yi should all be roughly equal. So roughly, xi minus yi all equal, because it was a random coordinate system, right? This is not a proof. I mean, again, we'll prove it carefully. So roughly, they should all be equal, and therefore, each xi minus yi. Now, if they are all equal, this was the length of x minus y whole squared. How would they be related to x minus y? Okay. There are d coordinates, they're all equal. Would I then have 1 over d times this, right? No, not quite, right? Because it's Pythagoras, so only the squares add up. So this will be 1 over root d. Okay. So this is correct. It turns out to be provable as a theorem. This is what was proved by Johnson-Lindner-Strauss in a 50-page paper, perhaps, in the beginning. And the difficulty was the random coordinate system. Okay. So this was difficult to do and prove, but later proofs did the following very simple thing. Gaussian, vector V. What that means is V is picked from the distribution normal 0, I. This is boldface. It's a vector, right? Picked from this. Then x minus y, dot product is it's of length 1. So what should it be? What should the dot product of this be in relation to x minus y length? Based on that kind of intuition, what would you expect? This and that. Same 1 over root t, right? Because this is again just a random x1 axis. Okay. Now, sometimes you need more solid estimate because we have many points and we want all pairwise distances. So what Johnson, Lind, and Strauss originally said is a random coordinate system, right? So the biggest difficulty here was that x2 had to be perpendicular to x1 and so on. But instead, it's enough to pick k of these, which are all independent normal 0, I. They won't be orthogonal, but we saw that they'll be close to orthogonal. That's enough. That turns out then that x minus y dot vi squared summed over these k would be roughly k over d times x minus y squared. So this is saying I take k coordinate directions and take the sum of squares. They're not quite. They're not perpendicular, but it doesn't matter, right? This can be carried out very easily, and we'll see that the proof is very simple. Proof is a few lines from the Gaussian annulus theorem. So a lot of sweat goes here into ensuring the orthogonality of these, but that's unnecessary. We can just take Gaussian vectors. They need not be quite orthogonal. This is a quantity we can easily find. Therefore, we might as well deal with this. So we'll prove that. We'll prove the next time. It'll be very simple again, as I told you, that this is true. And I'll probably give you a couple of applications of that.